Okay, welcome back again. This is Professor Elliott, and in this video we're going to be solving the common collector amplifier, and then we will go on to the Darlington pair. So it'll be very similar to our common emitter solutions. So anyway, let's get to it. Okay, so this is the schematic. Again, you will need a printed copy. However you get that is up to you to work with. And this is going to be, of course, our output. Sorry, drew the wrong spot. Going to be VO. Okay, so let's continue on. So, okay, all right, so we have the common collector. Notice that there's no collector resistor. Okay, everything else is your standard voltage divider. C1 is your input capacitor. C2 is your output capacitor, and there's no emitter bypass. So, okay, so write that down, and then we'll continue on. Okay, again, this is the Thevenin equivalent circuit for the for the voltage divider. And again, we need to solve for RTH and VTH as per usual. So RTH is going to be R1 parallel with R2. That equals 25 parallel 50. Okay, so that's 16.66 or 67. I don't care if you round it off or not, doesn't matter. So RTH VTH R2 R1 plus R2 times VCC, so that's going to be 50 divided by the 75 times 20, 13.33 volts. Okay, that's RTH and VTH. And again, those are the two values we just solved for. Okay. All right, R in base, DC resistance looking into the base of the transistor. So that's going to be beta DC times RE. Let's let that equal 120. So that's going to be 560 ohms times 120. So R in base equals 67.2. K ohms. Rn is looking to the voltage divider. So that's R in base plus RTH, so that's 67.2 plus the RTH was 16.67. So 67.2 plus 16.67. 83.87 k ohms. 83.87. There we go. That's good. K ohms. That's for RN. IB plus VTH minus BBE, which is 0.7. Excuse me. So that works out to be 150.59 microamps. And that's because it's a large value of R2. That's why so much voltage across it, why it's a little higher than normal. But what we've seen before, not normal. But okay, so that's the model. You get the formula from, and of course IC is IB times beta. Okay, so times 20 over 120, 18.07 milliamps. Okay, and if you work out IC sat, you'll find that's pretty close to the center. Okay, so we're good. Okay. AC model. Again, replace all the capacitors with short circuits and remove VCC, replace it with a short, redraw what you see. Okay, so we're calculating all these things, so take a copy of this before going on, please. Okay, so Z out is going to be then RE parallel with R3. And in this case, R3 is obviously the load resistance. So it's going to be 320.61 ohms. Z and base. Okay, we need R prime E. 25 millivolts divided by IE. So that was 25 millivolts divided by 18 milliamps. We worked out earlier. It was 1.38 ohms. Okay. All right. So just have to erase what's on the slide. Okay. So now we can go ahead solve for Z and base, and that's the resistance looking into the base. So let's go back a couple slides. Okay, so it's going to be, if we would ignore R prime E, which we're not, but if we ignore R prime E, it would simply be Z out times beta AC. Okay, so Z in base is approximately beta AC times Z out. Okay, and let's let the beta AC equal 160. Okay, so that's going to be 160 times 320.61 So that's going to be 320.61 times 120 equals 38.47 k ohms. Write this on my sheet. That's ignoring R prime E. Okay. However, you'll see the small difference, which is not a lot, truthfully. Including R prime E, it's going to be beta AC divided by R prime E plus Z out. Okay, so this is what I've shown here. Okay, so again, the output impedance again was the 320 ohms plus the R prime E 1.38 times the beta Okay, so that's going to be equal to 51.52 k ohms. Okay, so that's the value. Okay, that's slightly more accurate. That's the value that that we're going to carry forward. Okay, is that all right? All right. Yeah, good. Okay. Let me just write this number down. 51.52 k ohms. Okay, Zn. Again, back to the diagram. Always back to the diagram. Zn is equal to RTH in parallel Z in base equals what? Equals the RTH was somewhere the 16K, so 1 divided by 16.67K. In parallel was Z in base, 51.52. This is the input impedance looking into the amplifier, 12.59 k ohms, and that's the number we're going to go with. Z in equals 12. And just go back a couple of slides. And so you can see then Zn is just simply these two things. So it's a little messy in parallel with one another. Okay. All right. So everything else looks good. Okay. Okay. Voltage gain. So like we did with the CE amplifier, constant current source. Okay, and this time the collector is at AC ground. We do our AC model. R prime E, right? And So yeah, so R prime E is the AC resistance of the it doesn't go there. Sorry, I need more. Drew it wrong. Let's do it like that. Yeah. I'm gonna draw these out just in two little bits. I think this may be a little bit better. Okay, so this would be RL, which is R3. And this is going to be RE. Actually, made a resistor. And this is R prime E. Okay, so this is the actual emitter. And that's the base. Okay, so the formula for voltage gain in general terms is AV, and there's no negative here because the input and output are in phase, is equal to VO divided by VN. Vn, of course, is applied to the base. So you can see here, it's really the ratio between the resistances of RE in parallel with RL, which is Z out, and plus Z out divided by, well, let's just go to the next slide here. Let me erase that. Sorry, too far back. It's too complicated just to explain it in words. Okay, so let's try it. Voltage gain, there we go. Okay, so AV voltage gain is equal to the output impedance Z out divided by R prime E plus Z out. I'll just go back again to this diagram here. You can see if I were to erase those lines, so we can start fresh. So R prime E is really up kind of in the emitter right there. I've shown it actually here, and so it's really Z out in series with R prime E. If you want to include it. Anyway, so we're going to do it both ways. Okay, so this will be Z out, which was the 320.61, okay, divided by 320.61 plus R prime E. 320.61 plus equals 321.99. And if we simply divide those two numbers, so 320.61 divided by last answer. Again, there's no negative because they're in phase. So this would be 0.99. So the output is like 99.6% of the input. And so this is not used to provide gain. It's used to drive lower impedance loads, which the CE amplifier cannot do. So that's the exact gain. It's actually a slight attenuation. If you were to ignore, I'll go back to my eraser here. If you were to ignore the small contribution of R prime E, we can simply do that. So that would be Z out divided by Z out, ignoring R prime E. So we can say the voltage gain is approximately equal to 1, which, by the way, in decibels is 0 dB. Okay, so that's the voltage gain. So the output voltage VO is going to be AV times Vin. And so that's going to be, again, this is RMS, 2 volts, okay, times, should do it the right way around. AV is 1 times 2 volts. In actual fact, it's going to be 0.9957 times 2 volts. 1.99. So it's a very, very slight attenuation, but anyway, that's the output. Okay, so this is the exact and this is the approximation, but I mean they're virtually the same anyway. Okay, so let's go back now to here, and I want to erase here like that. Okay, good. So if the source we were to take into account RS, and we'll do an example of this in class. I'm just going to point it out to you, is that as even from the emitter side, the source resistance RS gets reduced by beta, so it's RS divided by beta. So including the source impedance, this is what the AC model of the emitter actually looks like. Okay, so I'll cover that in class. There's another handout somewhere on eLearn that covers that. But anyway, this is presentation just about the basic common collector. I'm just sort of pointing this out to you. But okay, so I guess that's about it. And thanks for sticking around, and we'll catch you soon. Okay, bye-bye. What? What do you mean no?